were going to be attending a day camp or a summer camp, I think here in Southern California. But unfortunately, that summer camp was canceled due to COVID-19. And when I found out that there's an opportunity to give this presentation to the Pomona Valley amateur astronomers, I thought I'd expand this and put in some additional really neat information. So that's the genesis of this presentation here. What I'd like to do is to start off at the beginning and just to give some, give a quick introduction to people about astronomy in general. And obviously, astronomy is the oldest of the natural sciences. It goes back thousands of years. I'm sure that if you were to travel back 1,000,000 years, you would still find human beings looking at the sky at night, wondering what those twinkling lights are. When you think about it, astronomy is the study of all the objects in the universe with one exception, and that's the Earth. And obviously, the reason why Earth is not included in astronomy is because that's our home, that's our spaceship, and we're observing what else is beyond the Earth here. All the information that we have received to date about those objects are from two sources: electromagnetic radiation and gravitational waves. Up until 1937, astronomy was all visual. In 1937, a radio amateur by the name of Grote Reber built a radio telescope in his backyard, and that was the beginning of opening up the spectrum to other frequencies. So instead of just being confined to the visible part of the electromagnetic spectrum, we now had the ability to do investigations in the radio waves. After that came investigations in gamma rays, X-rays, ultraviolet, and infrared. Now, what's amazing to me, as far as I'm concerned, is that for 1,000,000 years, we were confined to look at the stars just with our own eyes. And finally, in 1937, we have an amateur astronomer who opens it up to radio. But if you were to ask any astronomer today what the name of that man was, they would look at you with a blank stare. You would think that, if anything, he would be one of the most revered astronomers of all time. And I hope that from here on out, the members of the PVAA remember Grote Reber as the one who has opened up astronomy. Now, what I'm going to do here as I go through, we're going to be encountering some big numbers, and I'm going to be using scientific notation. So 1,000,000 is going to be 10 to the 6th. 1,000,000,000 is 10 to the 9th, and so on. One of the numbers that will pop out quite readily is 10 to the 21st. That's 1 sextillion. And shortly you'll find out where that comes up. So here's a quick chart that shows you the electromagnetic spectrum. We start on the left with the high frequency, high energy part of the spectrum called gamma rays. Then we progress to X-rays, ultraviolet, then the visible light, which is just a very small sliver in the electromagnetic spectrum. It goes from blue to red, red being the low energy, long wavelength part of the visible light. Then we have outside of that, we have infrared and then radio waves. Recently, starting in 2015, we have a new spectrum that has opened up to us. It's called gravitational waves. For a long time, it was conjectured that gravitational waves existed, but nobody knew for sure. It wasn't until 2015 with LIGO that we have now been able to do some kind of astronomy with gravitational waves, which is a huge breakthrough. 2015 was a very interesting year because that was the 100th anniversary of Einstein's general theory of relativity that predicted gravitational waves. So it was a really fine and fitting tribute to Einstein that on the 100th anniversary of the general relativity that we first were able to detect gravitational waves. What's interesting here is when you look at this chart that shows on the left the very high frequency, high frequency stuff. On the right-hand side, you have the low frequency, long wavelength. This basically covers the same frequency of and wavelengths as visible, or I'm sorry, the electromagnetic spectrum. So we have two spectrums that basically overlap, but they're completely different in nature. Okay, what I'm going to do here is I'm going to start off with Earth. And like I had mentioned, we are all astronauts traveling through space and time on a spaceship called Earth. Our spaceship is rotating. It's got a mass of 6 septillion kilograms. It's got a radius of 6,371 kilometers. It's got a rotational speed of 360.99 degrees per day. And at that rotational speed, at the latitude that we're at here in Southern California, we are traveling faster than the speed of sound. We are traveling at this moment 1,386.56 kilometers per hour. The speed of sound is 1,150 kilometers per hour. So if anybody's asked you how fast you're traveling, you can tell them, I'm going faster than the speed of sound. In fact, we're now traveling at Mach 1.2. What's interesting here is that before liftoff on the space shuttle program, the astronauts had a view of the inertial velocity on their screens. And the inertial velocity at Kennedy Space Center is basically the same as what we have here in Southern California. And their screens were telling them that they were traveling 1.3 while they're still sitting on the pad. So that was interesting. What we need, obviously, on our spaceship is something to maintain us. So what we have provided for us is 2 oceans. We got an ocean of air called the atmosphere with a mass of 5 quintillion kilograms. And what's lucky for us being astronomers is that that air is transparent to visible light. The second ocean that we have is the water ocean called the hydrosphere. And it's got a mass 260 times that of the atmosphere. So here we are. Here's a picture of our spaceship. We're located here in Southern California. At least that's where I am right now. I know that we have probably other people scattered across the United States right now, but this is where I am right now over on the left coast of the United States. Okay, now how do we go about observing celestial objects? Well, the first astronomical instruments that we use were very simple. There are our eyes and brain. Using these, the Babylonians were able to determine the lengths of the day, month, and year, basically to the same accuracy as what we have today, which is an amazing feat. The first major improvement was the telescope, and that wasn't invented until 1608. Telescopes, I guess you can view in 2 different ways. Telescopes are electromagnetic radiation buckets. They enable us to see far into space. The other way that you can look at them is that they are time machines. Because as it turns out, the farther back or farther into space you look, the farther back in time you see. So when you go out at night and you look at the moon, you're looking at the moon not as it is right now, you're looking at the moon as it was over 1 second, or actually over 2 seconds ago. So that's an interesting thing to think about. Obviously, when you look farther into space, when you look at Jupiter, you're talking about something that you're seeing that existed over an hour ago. You go and look at the star closest to the sun. That star, Proxima, had its light leaving over 3 years ago. So it's an interesting thing. It's an interesting thing for us as astronomers to know that our entire lives are spent by looking at things that happened in the past. A lot of people don't know who invented the telescope. It was Hans Lippershey in the Netherlands in 1608. And give this a thought. Before the invention of this telescope, we could see only one celestial body with a solid surface, and that was the moon. After the invention of the telescope, we had a huge improvement. We could now see two celestial bodies with a solid surface, and that was the moon and Mars. Now, obviously, that underestimates the ability of astronomers to see different objects. One of the hidden things in that statement is the fact that most of the planets that we normally would be able to see the surface of with a telescope are covered in clouds. So that sort of is a fudge type of thing, I guess you might say, when you say, well, we only can see two objects that have solid surfaces with the telescope. But anyway, distances that we see different objects in astronomy are so far away that we have measured those distances not in kilometers or miles usually, but in units of time that light has been able to go from one place to another. For example, a light second is 186,000 miles. A light minute is 11 million miles. 1 light hour is 670 million miles. 1 light day, the distance that light travels in 1 day is 16 billion miles. And the distance that a light can travel in the vacuum in 1 year is almost 6 trillion miles. So when I talk about light years coming up, think about the length of 1 light year being 6 trillion miles. So here I've given some distances in terms of those units. Earth to the moon is 1.28 light seconds, which means that the light that we get back from the moon is 2.56 seconds old, because we're talking about a round trip. The distance from the sun to the Mercury is 3.2 light minutes. From the sun to the Earth is 8.3 light minutes. From the sun to Proxima, 4.24 light years. From the sun to the center of the Milky Way is 25,766 light years. And from the Milky Way galaxy to M31, which is Andromeda, is 2.5 million light years. So that gives you an idea about some of the distances and time differences that are involved in looking at astronomical objects. For example, here's a diagram that shows the distances to the stars in Ursa Major, which is the Big Dipper. The stars, it turns out, in the Big Dipper are fairly close to the Earth. They measure from about 63 light years to 210. but they're not all at the same distance. They only appear together just by happenstance. They're all pretty much in the same field of view when you're looking at them, but just due to their positioning, they look as though they might be in the same, about the same distance away, but they aren't. Now here's Orion, which is a little bit further away from the Earth. We got stars that go from about, I think it's about 600, well, I guess it'd be about 300 light years all the way up to about 1,300 light years. And the closest one, let's see. Well, I got, unfortunately on my screen, I can't really see my right hand on the screen because of the video, but if you look at Orion at night, which is prominent in the sky tonight, you'll be able to see that on what looks to be his left elbow, which is, when we look at it, the star on the right upper part of Orion, that one is, I think that's right, y'all, I think. And that one is the closest of the stars in Orion. But you get over to the stars in the belt, you're getting in the area of about 1,000 light years away. And the farthest one is the Orion Nebula, which is right below the belt. That's at the tip of his sword. And that nebula turns out to be 1,344 light years away. So when you're looking at that nebula, you're looking at what the nebula looked like, not as it looks like today, but over 1,000 years ago. So we're now stepping out into the solar system. We've gone from the sun and the earth to the solar system itself. And it's interesting when you look at the solar system, you look at the objects that it contains and everything, and you got a pretty wide spread of sizes of objects. First of all, the diameter of the solar system is about 1.6 light years across. When you consider the Oort cloud with all of the comets, that encompasses a huge amount of space, going out to about 3/4 of a light year from the sun. The mass is about 2 × 10⁻³ kilograms, which is about 2 nonillions. So that's a huge amount of mass. The sun, it turns out, makes up 99.86% of the mass of the solar system. So it can literally be called, when you're describing the solar system, as basically containing the sun and a lot of debris. If you want to include one of the planets, you could say it contains the sun and Jupiter and a lot of debris. Jupiter, being the largest planet, has a mass of about 2 octillion kilograms, and that contains about 71% of the mass of all the planets. So our little spaceship is part of the debris orbiting the solar system. And when you measure the distance between the Earth and the very center of the solar system, it turns out to be 93 million miles. And when you work out the math, the orbital speed that we have is 66,600 miles per hour. So if somebody was to ask you how fast you're really traveling, you might say, well, I'm going at 66,000 miles an hour. What I think you might want to also remember here is that we're not really orbiting the sun. We're orbiting the very center of the solar system, which is the center of mass of the solar system. And here's a depiction of the sun and the planets. this is about the only depiction I was able to find on the internet that gave a pretty realistic depiction of the sizes of the planets. Unfortunately, most of the depictions, in my opinion, are worthless because they really don't do justice to the sun. But this is the one that I found that really does a good job, and you can see pretty much how those planets compare to the sun and to each other here. Okay, our next step is to go and look at the Milky Way. The Milky Way has a radius of about 50,000 to 65,000 light years, which means that it's about 100,000 to 130,000 light years in diameter across. The solar system is located about 26,000 light years from the center, and our orbital speed in orbit around the center of gravity of the Milky Way is 519,000 miles an hour. So there's another number that you could use if somebody was to ask you how fast you're traveling. 519,000 miles an hour in orbit around the center of the Milky Way. That means that we have an orbital period of over 200 million years, which means that we are right now approximately where we were 200 million years ago, which was the start of the age of the dinosaurs, which is kind of cool to think about. The total mass of the Milky Way is about 1.3 trillion solar masses. And astronomers have estimated that it contains about 400 billion stars and may contain up to 1 trillion planets. The star closest to the sun, like I mentioned, is Proxima Centauri. And it's an easy thing to remember how far away it is. It's 25 trillion miles. I measured it. So 85% of the total mass of the Milky Way, however, is something that we really don't know what it is. We call it dark matter. And I'll get into that a little bit later on. Here's a depiction of the Milky Way as we think it looks like, based on astronomical measurements and soundings with radio waves and visible and all kinds of other parts of the spectrum. This one happens to be looking from the north of the galaxy, what we call north. And in this view, the sun, the orbit of the sun I have depicted in blue, and we're traveling clockwise in this view. So we're going, if you look at the bottom here where I show where the sun is, we're now traveling to the left as viewed in this view here. And we're traveling, I believe it was, I think it's about 200 kilometers per second. So we're going at a pretty good clip here. One thing I noted on here is two things. If you notice, I have two thin lines that come up around the center of the Milky Way. That depicts the area of the Milky Way that we don't have any visual measurements of, because the center of the Milky Way is so bright, we just can't see what's on the other side. So we rely on radio waves basically to get the information about what is over in that region there. The other thing I show on here is a yellow circle, which is about 5,000 light years, I think, in radius, I think. I can't see on my screen what it is, but I think it's 5,000 light years in radius. And that basically covers, I would say, probably on the order about 95% of all the stars that we can see with the naked eye at night. So what you're looking at night is basically stars that are well within 5,000 light years of the Earth, and most of them actually are on the order of hundreds of light years away. I think that what I have on here is that about 1/3 of all the stars that we can see are about only 250, well, within 250 light years of the Earth. So it's not all that far that we can see at night. So that's where the telescopes really come in handy. Here's a depiction I wanted to show, is because people, I think, a lot of times think that we're in a smooth orbit around the center of the galaxy, and that's really not the case. We're actually bobbing up and down. And that bobbing up and down is basically due to us, coming up above the disk of the Milky Way, being pulled down by the mass of the disk, going down in one direction, then being pulled back up in another. So as we go around, we're bobbing up and down with a period of about 60 million years. So right at this time, it turns out that the sun is about 55 light years above the plane of the galaxy that we're in. And I think that it's going to be several million years yet before we get to the apex, before we start coming back down to the disk. One thing that's interesting here about the rotation of the galaxy is that the galaxy is not rotating as we would have expected based on Kepler's laws of gravitational, gravitation and motion of the planets. It turns out that when you look at all the stars that we can see, which are basically made of baryons, the basic stuff that we see every day on Earth, just ordinary matter, with the elements that we know about, you would expect that the stars would have a rotational velocity or orbital velocity that follows a curve like this as you go out towards the edge of the Milky Way. However, that's not what happens. What happens instead is that you reach a maximum peak here about 250, 260 kilometers per second, and then you basically level off or slightly decline as you go out. So obviously there's one of two things that are happening here. Either our theory of gravity is not quite right, or there must be something that's causing, pulling the stars out in the Milky Way to cause them to go faster than what we would expect them to do. And there's a big controversy that's going on now, or a big argument, I guess, amongst the astronomers as to which of those two options might be the cause. Is it due to our misunderstanding of gravity, or is it due to something that we're calling dark matter that's pulling on each of the stars in the Milky Way to cause them to go faster? So that's a big area of astronomical research right now, trying to get a handle on what that might be. Now, this is a very busy chart. It shows the characteristics of all the stars, or most of the stars in the Milky Way, covering the main sequence stars, the giants and the supergiants, the dead stars and the failed stars, giving the spectral type, the prevalence, typical temperature, luminosity, radius, and mass, and other things like that. What I'll point out real quickly is that most of the stars that we have out in the Milky Way fall in what is called the main sequence. In fact, I think there's something like about, I think there's something like over 90% of all the stars that we have been able to get information on fall within what is called the main sequence here. And obviously that's where the sun falls in there too. It's a yellow dwarf. It's a G-type star. And the G-type stars, like the sun, constitute about 10% of the stars that we have been able to get information on. However, most of the stars that we know about in the Milky Way are red dwarfs. And what's interesting about the red dwarfs here is that even though they are the most prevalent stars in the Milky Way, we cannot see a single one of them with the naked eye. When you go out at night, you're not seeing a typical star. You're seeing the stars that are bright and big usually, and they're atypical. But if you were to ask somebody, or if somebody was to ask you, well, what's a typical star? You'd have to say it would probably be like a red dwarf. Unfortunately, we can't see them. Now, like I say, this is a busy chart. What I would prefer is something like this. This is what's called a Hertzsprung-Russell diagram, or for short, it's called HR diagram. It was first derived independently by Hertzsprung and Russell back, I think, about probably maybe 1920s or so. But I think, in my opinion, this is probably the single best chart that has ever been produced in history, especially in the field of astronomy, because a chart like this can tell you a whole bunch of stuff. First of all, let me tell you what this is all about. If you look at the bottom here, it gives you the spectral classes. It goes from O to B to A to F, G, K, and M. The O stars over on the left are the big ones and the hot ones. And the ones over here on the right, the M stars, they fall into two categories. You got the giants and the dwarfs. This is where the most prevalent stars in the Milky Way reside is in the bottom right part of the chart. The vertical scale is luminosity. So luminosity is nothing more than the brightness of the star. And this is what's called absolute magnitude. This is the true brightness of each of the stars when they're plotted on this plot here. So over here in the bottom right, you have the cool, small, red stars. Let me just point out real quick that each one of these classes, the O, B, A, F, G, K, and M stars, are correlated to the temperature of the star. So if you go over here to the O stars, those O stars have temperatures on the order of about 40,000 degrees Celsius. All the way over here to the M stars, you're down to only about 2,500 degrees. So there's a big difference between the O stars and the M stars going, you got the very hot ones over here on the left, you got the very cool ones on the right. On the bottom, you have the very dim ones, you have the very bright ones on the top. But not only that, you also can determine the approximate diameter by looking at these lines over here. You have lines of constant diameters going from the bottom left to the upper right, starting off with 1/1000th of the diameter of the sun, going all the way up to the supergiants that have diameters on the order of 1,000 solar diameters. Not only that, but you can also, if it turns out that the star that you're looking at falls on the main sequence, which is this line of stars in the middle and going down here to the lower right, you can also estimate their lifetimes. So if you go over here to the blue giants, you can see that they have a lifespan of no more than about 10 million years. coming over here where the sun is, which is over here in the sort of like the right-hand center of the plot, you got stars on the order of about 10 billion years of a lifespan. If you go down here to the red dwarfs in the lower right, you have lifespans on the order of 1 trillion years. So the rule is basically is that if you're a hot star, you got a short lifespan. But not only that, you also have in here an estimate of the solar masses if you're here in the main sequence. Of the hot blue giants have solar masses on the order of about 50 solar masses. Down here in the red dwarfs, you have solar masses only about 1/4 that of the sun. So as you go towards the left, you have bigger and bigger stars in general. So this diagram, in my opinion, is a real neat one. I think this is something that all astronomers should have and understand. One thing I drew on here, which usually doesn't show up in a diagram like this, is the instability strip. It turns out that if you have a star and you plot it on the HR diagram and it falls within this rectangular area, that star usually is a variable star. And if you look in here, you'll notice that Polaris is right there in that instability strip. And Polaris is what's called a Cepheid variable. And Cepheid variables are very important stars because those are standard candles for astronomy. They're used to determine the distances between us and other galaxies. And so Polaris, being one of them, could be construed as being a standard candle for the Milky Way. So anyway, I think that this is an important chart, and everybody, at least in the PVAA, should have one and should understand what it's all about. Now, what I'm showing here in this chart is the star spectra. So if you start over here on this middle part of the chart here, and you look at the bottom, I have the same spectral classes, O, B, A, F, G, K, and M. By the way, you can always remember that because those are the first letters of the phrase, "Oh, be a fine girl, kiss me." So now if you're a girl, obviously you don't want to say that. The girls will tell you that it means, "Oh, be a fine guy." I'm sorry, yeah, fine guy, kiss me. So depends on what whether you're a guy or a girl as to how you want to remember this. But that's the way that most astronomers can remember the sequence for the spectral classes. But anyway, like I had pointed out, the sun is a G-type star. And if you look what that spectrum looks like, you can see that it covers a lot of the visible spectrum pretty well, going from the blue to the green to the yellow to the orange and the red. You go over here and look at the O and B stars, those are basically blue stars. So that they all are pretty much looking like blue stars when you look at them in a telescope. Over at the M stars side, the M stars pretty much are in the red part of the spectrum. So they look red. If you look at the G stars, however, the G stars have a mean wavelength of 0.55 microns. Well, 0.55 microns falls in green. And that's where the sun is. So the sun really is a green star. Now, one thing that people sometimes ask is, why aren't there any green stars? We have blue stars. We have white stars. We got yellow stars. We got orange stars. We got red stars. What happened to green? Well, it turns out that the reason why the star or the sun does not look green is because of what I said before. The spectrum is spread out so that it's basically covering all the visible spectrum pretty well. And as a result, when you combine all the various colors in the spectrum, you come up with white. So that's the reason why. But I got some interesting things here over on the left-hand side that I'll point out. The effective surface temperature is about 6,000 degrees Kelvin. It's got a bolometric luminosity of something like about 384 septillion. We got a total solar power that's received by the Earth that is something like 174 quadrillion watts. And that is an interesting thing. We have, sometimes, you hear people talk about an energy crisis, with gasoline prices going up and stuff like that. But look at this number. This number, the 1.742 times 10 to the 17th watts, is the amount of sunlight energy or power intercepted by the Earth. If we could capture only 1% of that and use it, that would cover our needs for a long time. So that's something to consider. The emission rate of photons from the sun is outstanding. 1.8 times 10 to the 45th photons per second. That's an astounding number. And the sun is paying the price. It's paying the price by losing mass. And the mass that it's losing is 4.28 billion kilometers every second. Now, it seems like a big number because for us, a billion can be, looked upon as a really good sized number, but that's just basically a very small number for the sun. I think that the sun loses, the time that it would take for the sun to lose the mass of one Earth would be something like about, well, I think it's something like about 600 million years. So the sun can afford it, at least for now. Okay, now we're stepping from the galaxy to the local group. The local group is a group of galaxies that are pretty much in orbit around the same center of mass. And it consists of the Milky Way galaxy, which is where we are, and the Andromeda galaxy, which is M31, plus a bunch of dwarf galaxies. The total mass of all those galaxies is about 3 trillion times the mass of the sun. Now, the Milky Way, just like all the other galaxies in the local group, is in orbit around the center of gravity of that local group, and that turns out to be 112,000 miles an hour. So here again, this is something to consider when you're trying to figure out what your real speed is when you're traveling on our spaceship through space and time. It turns out that the two largest galaxies in the local group are basically coming towards each other. Just this last month, it was determined that that Andromeda and Milky Way are on a collision course, and they will be hitting each other sometime in about 4.5 billion years. So get prepared. Current distance is 2.5 million light years away. We're approaching Andromeda at a speed of 246,000 miles an hour. So hold on. So here's a depiction of the local group. It's centered on the Milky Way in the center. you can see the Milky Way relative to Andromeda. Andromeda is in the upper left-hand part here. All the other galaxies that are in the local group are depicted here too. But what's interesting in this plot is if you look at these ellipses are going out at a clip of 2 million miles, 2 million light years intervals. So this first one, you're going out 2 million light years. The second one, it's 4 million light years. Next one is 6 million light years. So we're now talking about distances on the order of millions of light years here. Okay, now we're going to be stepping out up to the big time here. I'm going to be talking about the observable universe. The universe, as we have found out, is 13.8 billion years old. This number came about just within the last 15 years. It was determined pretty accurately with a spacecraft by the name, or called WMAP, which I think stands for the Williamson something or other, but that was the spacecraft that did the very first detailed, got the first detailed mapping of the cosmic microwave background. We had another spacecraft that preceded it. It was called COBE, C-O-B-E. But WMAP came along, did a better job. And then there was another one built by the European Space Agency, or sent up by the European Space Agency, called Planck. And that was even better than WMAP. But they all pretty much agreed in the final conclusions that the universe is right around 13.8 billion years old. The observable universe is 93 billion light years in diameter. Now, how in the world can you see stars that are over 46 billion light years away? And the reason why we can say that is because the universe is expanding. When you look back in time, when you look back in space, the farther back you look, the faster objects recede away from the Earth. And as a result, even though we can detect light from some object that was, a billion light years away from us at that time, since Earth, the space and time is expanding, that object that we looked at that looked to be like 1 billion light years away is now over 3 billion light years away. So when you actually determine how far far away an object is today relative to where it was when it emitted the light that we're seeing, it's a lot farther away. And that, as a result, results in an observable universe that is a lot bigger than just 13.8 billion light years in radius. So anyway, the co-moving volume in, as we are all moving together in space, which is expanding, the co-moving volume that all these objects are embedded in the observable unit consists, or has a total volume of 100,000 cubic giga light years, 100,000 giga light years. So it's a huge, huge volume, as you'd expect. It contains 3.57 times 10 to the 80th cubic meters, which is a fantastic number. Talking about the contents of the observable units, or observable universe, they come in 4 different types. The first type is dark energy. That constitutes what we believe to be 71.7% of the total mass energy of the observable universe, and we have no idea what it is. But we do know that there's something that causes the acceleration of the expansion of space-time, and we're calling it dark energy. What that may be, nobody really knows what that would be. The second category that objects fall into, or the content of the observable universe, is non-baryonic cold dark matter. That makes up about what we think is 23.2% of the total mass energy of the observable universe. And again, we have no real idea of what that is. In fact, there's a big controversy that's going on, and this is another, like I mentioned before, this is an area that is in intensive research right now, trying to determine what that cold dark matter is. But what we do know, like I had pointed out, it affects the rotational curves of galaxies. And there's something that we think called dark matter, which is causing that to happen. The next category is baryonic matter, which is basically the matter that we're all used to, the elements that constitute the sun and the earth and all the planets and everything that we can see. But that only accounts for 4.36% of the total mass energy of the observable universe. Now, it turns out that when you look at that matter, 98% of it is nothing more than hydrogen and helium. So when you ask, well, what makes up the observable universe when it comes to just basic matter that we know about, you can just say, well, it's just basically hydrogen and helium. That's it. Hydrogen and helium, and some debris. Well, guess what? We're part of that debris. The mass of that baryonic matter in the observable universe is about 1.45 times 10 to the 53rd kilograms. That's a huge number. There's about 2 trillion galaxies that is made up of that stuff. There's about 71 sextillion stars. Remember, I told you to look for that 10 to the 21st because you're going to see it. So there's 70 sextillion stars in the observable universe, and that is a truly large number. The number of atoms, however, dwarfs that. The number of atoms is estimated to be somewhere between 10 to the 78th and 10 to the 82 in number, and that is huge. The number of fundamental particles is even bigger and can be up to about 10 to the 85th. So that's a huge number. I don't think that there's even any nomenclature that goes along with a number that big. Then the next category is radiation, and that takes up just a small amount of the total mass energy, but a huge amount of the number of entities in the observable universe. One thing to think about when it comes to radiation is this. Every second of every minute of every hour of every day, there's 50 trillion solar neutrinos that pass through your body. That's an amazing number and something to think about. Not only do they pass through the human body, but they pass through the earth as though it's not even there. They're that small and that energetic that they go unimpeded even by the earth. Now, when you talk about the observable universe, there's something that's called the CMB. That's the cosmic microwave background. And I think that Ron was talking a little bit about that before the presentation here. The background radiation that we can detect, which is in the microwave part of the spectrum, is what we think is the leftover radiation from the creation of the universe, which happened 13.8 billion years ago. And if you look at how fast the Milky Way is traveling relative to that background radiation, the Milky Way is traveling 1,400,000 miles an hour. The speed of the sun relative to that same background radiation is 823 miles or 1,000 miles an hour. And to me, the CMB being, if you were to place your coordinate system or your reference frame with that, that would probably be about as close as you can come to a true inertial reference frame. So the true velocity of the sun and the earth going through space and time is really 823,000 miles an hour. So when somebody asks you how fast you're traveling, that is the true number. That's really something to think about. Here's a depiction showing the observable universe. If you look at this, the whole entire picture basically represents the whole universe. The yellow circle represents the observable universe. And that magenta or pinkish circle in the center, that represents the present reachable distance that we can see with our telescopes. So this sort of puts in perspective where we are in the whole universe. And to think that the whole universe could possibly be infinitely large is mind-boggling. Just thinking that how big the observable universe is, and to think that the whole universe could be millions of times even bigger is just incredible to think about. So I talked about the cosmic microwave background. This is, I think this is something that was produced based on data from the Planck spacecraft. It shows the microwave background, and you see the blue and the orange and the red in here. Those represent changes in basically what you might call temperature. This background, I think, is, what is it? I think it's 2.75 Kelvin is what they have estimated to be the residual temperature left over from the Big Bang. And these color-coded dots are just tiny fluctuations or differences from the mean temperature, very small though. So the universe in general is very smooth. It has pretty much the same temperature no matter where you look. And this represents the whole shebang in one picture. Now, I talked about the WMAP satellite. This is a depiction of it doing its observations, looking all the way back to the CMB, which basically is what you're looking at the universe as it was 375,000 years after it was born. And as you look at this, the middle part of this picture depicts all of the observable universe that we can see. And if you look at the outer rim of this, it's got a curve that's going up, which shows that it's expanding, and not only expanding, but its expansion is accelerating. But the whole expansion is, like I said, 13.8 billion years old, and we're still going. Okay, next chart. One thing that's interesting that a lot of people have heard about, I think, is Hubble's law. I mentioned that the universe is expanding, and this is how we know. A lot of measurements were taken back in the 1920s and 30s. And what Hubble did was he took the measurements, and this is basically based on changes in well, basically in the redshift of the various emission lines in the spectra of stars in galaxies that are thousands and millions of years, millions of light years away. What he did was he plotted the distance that he thought these galaxies were from us versus their velocity. And lo and behold, it came up with a straight line, and that straight line shows how fast space-time is expanding. And you've heard of Hubble's constant. Hubble's constant is nothing more than the slope of that line. And it turns out that the slope of the line is something on the order of somewhere around 70 kilometers per second per megaparsec. Now, megaparsec is another big length of time, or big length of distance. A megaparsec is about 31 quintillion, what was it? I think it was in kilometers is what that was. But it's a very long distance. And so it's very, you have to be very careful when you come up with your plot and plotting the line of the slope here, because any slight error can throw you off quite a bit. So there's been a lot of investigation on Hubble's constant. There's a big argument that's going on right now. There's one group that is claiming that Hubble's constant is something on the order of maybe like 67, maybe 66 kilometers per second per megaparsec. And there's another group that has data that shows it to be higher than that, somewhere around 72 to 73. But that's another area of big research in astronomy that's going on right now. One thing I'll point out here, I have an equation here that shows what the velocity is of an object that is so far away from us in distance. It's equal to c times z. C is the speed of the light and z is the redshift. And that in turn is equal to Hubble's constant times the distance away from us. You have to be very careful with this. If you actually do try to use this, it turns out that the c times z is good only for short distances. When I say short distances, I'm talking about, thousands of, maybe, several million light years. But when you're talking about billions of light years, it gets more involved in this because general relativity kicks in and you have to be careful. But so a lot of plots that you see do not show the distance. You won't have a plot that shows, let's say, speed versus distance. It'll be speed versus z. And the z part comes in only because people have their own models for converting z, the redshift, into well, I guess you'd call that a constant. But anyway, I thought that was an important plot to show. So what we have done in recent years is we have sent up satellites to take, get information on all the galaxies that we can get our hands on through the observable universe. And one of those was called I think it was Sloan. I think that's a Sloan project that used satellite data to gather information on millions and millions of galaxies. And they have printed that out over here on this plot right here. What they did was they had the satellite look into the northern part of the sky above the Milky Way, just a thin slice, going, looking at as far as it could, above the Milky Way. And they did the same thing in the southern part, looking south of the Milky Way and getting the same type of data. And they plotted it all. Those two slices are both plotted on this same plot, and it's plotted versus the redshift. And that redshift goes out to 0.7 on this plot here, which I compute to be about 8.25 billion light years. So it just gives you an idea, just looking at two small slices through the observable universe as to how many galaxies there may be. Just incredible. So to give you an idea how big these numbers are, I thought it would be interesting to show you how big the number is for the number of stars we think there are in the observable universe. And like I mentioned, we believe that there are 70 sextillion stars. Okay, so that's a big number. What I did was I looked at the land surface of the area of the Earth and found it to be 150 trillion square meters. Then I estimated how many of grains of sand there might be in a cubic meter. And looking on the internet, I came up with a bunch of different estimates, but I think that a good estimate would be somewhere around 18.5 billion grains of sand per cubic meter. I know that's an accurate one because my daughter and I, Marissa, we went out to the beach last Saturday, and we counted out all those grains, and came out to be exactly 18.5 billion grains of sand per cubic meter. So what I did then was I did a computation to see how much, how deep would the sand be if you were to dump 70 sextillion grains of sand, each one representing a star. How deep would that sand be on all the land, covering all the land surface on the Earth? And it turns out to be 1 inch. So when you think about it, think of all of North America, all of South America, all of Europe, all of Asia, all of Africa, all of Australia, all of Japan, all of Greenland, all of the land surface on the Earth covered by 1 inch of sand, each one of those sand particles being really itsy bitsy, and each one representing one star. That is approximately the number of stars in the observable universe, which I think is astounding. However, I thought of another way of looking at this. I was wondering, well, how much water would you have to have that many atoms in your bucket or lake or whatever? So I did the same type of computation. Turns out that I know that there is the Avogadro number of molecules in a mole of water. Well, a mole of water is 18 grams. So you look at the atomic number or atomic mass of oxygen and hydrogen, comes out to be 18. So a mole of water is 18 grams. Well, in each in each molecule of water, there are 3 atoms. So there's 3 times Avogadro's number in a mole of water. So I asked myself, okay, how many of those molecules or atoms would be in 1 drop of water? Well, a drop of water is 0.05 milliliters. The density of water is 1 gram per milliliter, which means that 1 drop of water has a mass of 0.05 grams. So the number of atoms in 1 drop of water, it turns out to be 5 sextillion atoms per drop. So what you need to do is you need to have 14 drops of water to have enough water to have the same number of atoms of, atoms in that amount of water to equal the number of stars in the observable universe. So 14 drops of water is all you need to have to match the number of stars in the universe. So there's one part of this that says that this is a huge number. There's another part that says it's still a small number. So you take your pick. Now I'm just going to wrap this up real quick with one observation. A lot of times people will say, well, okay, so what? Why should this matter? Who cares about stars? Why should I need to worry about, getting involved with stars? Well, here's the answer. Look at the elements that constitute not only the Earth and the stars and the planets, but us. We're made of basically hydrogen, carbon, and oxygen. Where do they come from? Well, this chart, this is the periodic table, which shows where each of those elements came from. And it turns out that they all were formed either in the Big Bang or in stars themselves. There are a few in here that are actually were produced in cosmic ray fissions, but most of them were formed in stars. And we're made of star stuff: carbon, hydrogen, and oxygen. And to think that we are made of the same stuff as stars is incredible. And I think that this goes to show that this basically means that we are the universe's way of understanding itself. And this is another perspective, I think, that astronomy provides for people that most people would never otherwise know about. And I think that's a good reason for being an astronomer and getting involved in understanding more about this universe that we're standing in. That's it.
Well, thank you. Let's see if I can unmute everybody here and participants here.
Oh, was I supposed to hit that?
So I want to thank you.
The Zoom meeting, click on it. Just click on the bar.
I have a question for
Right there.
Ken.
Okay.
Ken, it's Laura. I don't have my video on.
Okay.
So my question was, when did they start measuring light years as light years?
Well, light years obviously came about after we found out how fast light traveled. And that's where Michelson and Morley came in. And that was early 20th century. I would imagine that the light year measurement probably came in the first half of the 20th century. Probably, I would imagine sometime like around 1920, maybe, right around in there. I'm not too sure when the Michelson-Morley experiment took place, but it was probably shortly after that time.
Okay, they must not have had. I was thinking, maybe as Hubble's discovery, but he had that measurement already, I think.
Well, what he did was he had basically redshift information. And, to be fair, a lot of people credit Hubble with Hubble's law and everything, but in truth, that was a huge effort by a lot of different people. He'd never made any measurements of redshifts. He got his information from other people as to how much each galaxy, each of the stars and each of the galaxies had in terms of redshift. And he was the one who put it together, correlating the redshift to distance and then distance versus the speed, and was able to come up with Hubble's law. But yeah, I think when another thing too, when Hubble first came up with his Hubble's law, that was on basically a fairly small sampling of galaxies, and it was also galaxies basically that were pretty close to Earth. When you plot Hubble's initial graph that shows his his basic first Hubble law graph onto a modern graph that covers galaxies out, billions of light years, it shows up as just a little pipsqueak in the lower left-hand corner, just a very, very small amount of data that he had at the time. But I think that most of his measurements when it came to velocity was not in terms of light speed, it was in terms of kilometers per hour.
You were describing the bump as the Earth travels around the center of the Milky Way galaxy. That number of 60 million years seems to correlate with the ice ages and the period of an ice age.
Now, I'm not too sure when it comes to ice ages, if that's the case. Are you sure about ice ages? Because, the last ice age was about 10,000 years ago. It wasn't all that long ago. I'm not too sure.
There's been like 5 major ice ages, and the period in between them is 2 numbers. One was like 41,000 and the other one was 100,000, depending on which interpretation you were listening to. In between it, we're in an interglacial period right now.
Okay, now it sounds like what you're doing is you're talking about thousands of years, not millions of years, though, right?
I've pulled this article out of the Scientific American, and what I'd like to do is look at it and be sure of the numbers.
Yeah.
But I have it available right in my desk here.
Yeah, there's data like this that people have used to support their arguments about cyclical events in Earth's history. When it comes to ice ages, I think that's probably not the case. But look it up, check out your numbers and see if that's correct. But yeah, I think that if I'm not mistaken, you're basically 3 orders of magnitude off. Instead of 60 million light year cycles, we're talking about maybe 60,000 light years, or yes, 60,000 year cycles.
There's a video on in NASA talking about size and distances, and they said that if you could shrink the Milky Way to fit within North America, so now the Milky Way is the size of North America, that our solar system would be the size of a quarter.
Yeah.
You're
Yeah,
going,
it really
darn.
gives you some. Well, see, that's the thing about astronomy, obviously. It really puts you in your place. You go over to Griffith Observatory and they have the whole solar system basically laid out in the front lawn. But, just the solar system itself, the orbit of Pluto, with the sun being the size that they have right there in front of the front steps of the observatory, I think that Pluto's orbit goes way out so big, so far away that they couldn't even fit it in the front lawn there. It just goes way out. But that's the thing. It's just mind-boggling. It's very difficult to try to wrap your mind around these numbers when you talk about distances, velocities, sizes. It's just amazing.
Well, Griffith is going to reopen really soon. They're going to be open on Friday, Saturday, and Sunday. They haven't decided on an official date, but they allowed us. I got to go to the first show of the planetarium since they closed down for COVID, and they opened it up for the Griffith Foundation and the Planetary Society. So I went, and so it was open for 2 hours last
Excellent.
Thursday,
Excellent.
and you had to have a ticket, but it's going to be nice to see the stuff reopening like that. I want to go visit the shuttle again and go visit Griffith and
Yeah, I
pretty
agree
soon
with
we'll
you.
be able to meet. I don't think we're going to be able to meet until school starts. It depends on the university or the college. But yeah, it's one thing about distances is it, like you said, it's amazing. You're just trying to figure out distances, and it's just mind-boggling. It truly is.
Yeah.
So I want to thank you.
Oh, yeah, sure.
Yes.
Thank you very much.
Yay.
Yay.